Today, we want to review our important angles. So we want to know sine, cosine, and tangent of what it comes down to in order is a 30, 45, and 60-degree angles. The reason that we want to know this is that we want to expand our trig functions to go beyond just acute angles. Right now, all of our trig function stuff has been used to solve right triangles, but the trig functions can be used for more than that. And the first step in expanding our trig functions beyond right triangles, or just triangles in general, is to learn some common values that we need to know. So let's remind ourselves of the ratios in these triangles. The important thing is that the angles are all set, and we're interested in the ratios of the sines. The ratios that we usually use in the 45, 45, 90 triangle, the ratios are 1, 1, and the square root of 2. So the two sides opposite the 45-degree angles have a measure of 1. And then the hypotenuse will be a square root of 2, which is approximately a number that we should know. So we should recognize the square root of 2, which is why we have calculators. So the square root of 2 is approximately 1.414, and we should know it that far. So this is approximately, I just use equals for approximately. A little lazy on my part, but the squiggly ones just bug me. So the exact value of the hypotenuse will be the square root of 2, and the approximation of the nearest thousandth will be 1.414. That's a number we should recognize. So in the 30, 60, 90 triangle, we got that by cutting in half an equilateral triangle with a side length of 2. So we make the hypotenuse a full 2. Opposite the 30-degree angle is a 1. Opposite the 60-degree angle is where we get the square root of 3. And we should recognize the square root of 3 because it's one of our tangents. And we're going to recognize the square root of 3 as 1.732. So that's a number that we should just remember. So now that we've said it once, we'll remember it forever because that's how people think math classes work. So square root of 3 is 1.732. An important thing to note when in the category of solving triangles, the biggest side is opposite the biggest angle. The smallest side will be opposite the smallest angle. So if we make an error in calculation, and this happened on some of our quizzes, if we make an error in calculation, we find out that the hypotenuse is 2, and we calculate the side opposite the 30-degree angle as being 12, something has gone wrong. Because the hypotenuse in a right triangle, the hypotenuse has to be the biggest angle. Sorry, the biggest side, because it will be opposite the biggest angle. So biggest angle opposite biggest side. Smallest angle opposite smallest side, which is why I wanted to throw in the approximations to see that the side opposite 30 is 1. That's the smallest angle. And so the smallest side is opposite that. Opposite the 60, the middle angle is the 1.732 or the square root of 3. So that's the middle-sized side. That is the Jan side. And then the Marcia side is opposite the 90, and that's the hypotenuse. It gets the special name because Marcia, Marcia, Marcia. I don't think anybody remembers what the Brady Bunch is, so I'm probably gonna have to update my reference at some point. All right, you're just gonna have to deal with this. You have a Gen X teacher, so we were raised by our television sets. What can I say? So we wanna combine this with all of our sine, cosine, and tangent. So sine opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent opposite over adjacent. Oops, my second monitor just went out. There we go. So if we want to, so what we want is the sine, cosine, and tangent of 30 degrees, of 30 degrees, 60 degrees, and 90 degrees. We also want to know the sine, so 30, I left off the 45. I said 30, 60, 90 because I was looking at this at the time. Good thing I'm not editing this video. So we want to know sine, cosine, and tangent of 30, 45, and 60. That's going to form a basis for when we expand these beyond acute angles. So we just have to remember these. Sine of 30 is opposite over hypotenuse, or 1/2. Cosine of 30 is adjacent over hypotenuse, or √3/2. And tangent of 30 is opposite over adjacent, or 1 over the square root of 3, which we will sometimes write as √3/3. In the middle, we have 45, so we should know the sine, cosine, and tangent of 45. So sine of 45 is opposite over hypotenuse, 1 over the square root of 2, which we usually write as √2/2. Cosine of 45 is adjacent over hypotenuse. So we also get another √2/2. Tangent of 45 is opposite over adjacent, and so that's just going to be 1. And then we want to know sine, cosine, and tangent of 60 degrees. So sine 60, cosine 60, and tangent of 60. Sine of 60, gonna have to go into this one, is opposite √3 over hypotenuse 2. Cosine of 60 is adjacent over hypotenuse, so 1/2. It's important to note that when we have sine and cosine of complementary angles, those will be the same. Sine of 30 is equal to the cosine of 60. Because what the one is opposite the 30-degree angle, and one is adjacent to the 60-degree angle. So if we replace the 30 and 60 with any complementary angles, the opposite side of an angle is the adjacent side to the other angle. And then tangent of 60 is opposite over adjacent, so in this case, just √3. So here are 9 values that we just have to carry around with us forever. Now that I've written them one time, we will remember them forever, because that's how human memory works. At least that's how a lot of teachers think it works. It's of course not how it works. We have to look for patterns. Here's the way that I like to remember it. Actually, I don't know if this is the way that I like to remember it. This is just the way that I do remember it. I always remember that sine of 30 is 1/2. That's the one that I always write first. I don't know why. It's the one that I picked. I remember that going 30, 45, and 60, it's √1/2, √2/2, and √3/2. I know we don't usually write √1/2, but it makes it a pattern. √1/2, √2/2, √3/2. That's 30, 45, 60 going across the signs. Then I remember how they're related to each other. So the cosine of 30, if we count 30, 45, and 60 on cosine, it just goes the other direction because of the complementary angle thing that we talked about. So the cosine of 30 is √3/2, cosine of 45 is √2/2, cosine of 60 is 1/2. It's the same 3 values, √1/2, √2/2, √3/2. Those are the ones that I remember. For the tangents, I always remember that tangent of 45 is 1. And I remember the decimal equivalence. √3/3 is smaller than just √3 by itself. So tangent of 60, since tangent has a numerator that's the opposite, the bigger angle corresponds to the bigger value. Tangent of 60 is √3, the bigger one. Tangent of 30 is √3/3, the smaller one. Then it's just a matter of remembering decimal equivalents of all these. So √2/2 2. If we remember that root 2 is 1.414, that helps us remember that root 2 over 2 is 0.7071. And as usual, I did not leave enough space here. But 2707 is 1.414. So that's how we can remember those two connected. If we want to remember root 3 over 2 as 0.8660, so since we're already remembering root 3 is 1732, half of that is 0.8660. So that'll help us remember which one is which. We already know that square root of 3 is 1.7. So if we divide that by 3 to get at the tangent of 30, 0.577. 0.5774 because I'm writing 4 significant digits for whatever reason. These are just the decimal approximations. As soon as we grab our calculator, we are looking at an approximation of the value. When we're writing expressions with square roots in them, we're thinking of the exact value. Any questions? So these are 9 values that we want to remember all the time and forever. Any questions? All right. So here's what we want to do now. We want to take these trig values and we want to start applying them to angles larger than 90 degrees. So we want to apply these trig values to angles larger than 90 degrees. We want to apply trig functions to all the angles, not just the acute angles in right triangles. All right. So what we're going to do is we're going to look at the unit circle. We're going to look at the Cartesian plane. We're going to look at the rectangular coordinates, X and Y, and we're going to look at the unit circle and start reading these angles all the way around the unit circle. So let's look at the unit circle. So the unit circle is going to be, just pretend this is a circle. I don't have my circle machine. Clearly I don't have a steady hand, it's all wobbly. I don't know if that's a more coffee problem or a less coffee problem. We're going to put the circle on a set of coordinates, X and Y, and the circle is going to have a radius of 1. So the unit circle has an equation x squared plus y squared is equal to 1. There's a circle, radius 1, centered at the origin. we're going to use this to build angles. So theta equals 0 is going to correspond to the x-axis, the positive x-axis, and we are going to measure positive angles counterclockwise from the positive x-axis. So I'm going to draw it in the second quadrant because we need to break out of our first quadrant. Theta is going to be measured from the positive x-axis counterclockwise. So this is how we're going to establish angles bigger than 90. So theta measured from the positive x-axis. So what we're saying is that here on the x-axis, that's where theta is equal to 0 degrees. Counterclockwise is the positive direction. Counterclockwise is positive. So we're going in the positive direction when we go counterclockwise. So what that means is that we'll measure starting at 0 here on the positive x-axis, going counterclockwise. When we get up to the y-axis, that's where theta is equal to 90 degrees. If I keep going around, when I get to the negative x-axis, now we're at theta equals 180 degrees. And then if we keep going, way down here, we've got 90, 180. Here's where theta is equal to 270 degrees. And then the interesting thing happens with these circles. If I get all the way back to the beginning where we're at 0, this is also where we'll find 360 degrees. Going around counterclockwise. 0, 1, 2, 3, 4, 5, up to 90, 91, 92, all the way up to 180, 181, 182, 183, all the way up to 270, and so on up to 360, where we can keep going or just start over. It's just a copy from 0 to 360. We just keep going around. It's just another copy. So the positive direction is counterclockwise. That means that clockwise is the negative direction. So if I start here at 0, I can go backwards, which is clockwise, and this 270 degree angle is also a negative 90 degree angle. If I keep going negative, the positive 180 is also a negative 180 degrees. It's really important to put the degrees here because we wouldn't want to say that 180 and negative 180 are the same thing. And then if I keep going up here at the top, theta is going to be negative 270 degrees. So this 0 can also be negative 360 degrees. So we have positive and negative angles. What we want to recognize is that however big or small our angle is, it'll always correspond to an angle between 0 and 360. There's always going to be some representation in that first circle, in those first 360 degrees. So if I have a 1,000 degree angle, that's clearly been around the circle a couple of times. So if I have a 1,000 degree angle, I start subtracting off full circles. That's 2 full circles. A 1,000 degree angle will be at the same place a 280 degree angle is. So a 1,000 degree angle will go around once, twice, and then 280 more degrees and be somewhere down here, a little past the 270. So what we're doing is we're creating a number line, not that just stretches on forever in both directions, but just kind of has the positive x-axis in the middle and goes positive forever around the circle, and the negative forever, but around the circle rather than stretching out towards infinity. Any questions? All right. So that's step number one. Establish the environment. This is like the world building phase. This is when your DM says, okay, this is what it's like in this particular world. Let's see. Now, let's talk about how some things work. So we've talked about the unit circle. We want to combine this with right triangles. We want to take the right triangles plus the unit circle to get at these angles that go beyond 90 degrees. So next step 2, put right triangles into the unit circle. We're going to put right triangles into the unit circle. Here's the important thing to remember about when drawing a right triangle into a unit circle. The radius of the circle is a hypotenuse. Oh, wait, no, I'm sorry. Skip that. I should edit this part out. I was thinking of a lecture that I'm going to be giving later on this week. Here's how we're going to put right triangles into the unit circle. Let's go and draw a unit circle again. That was a little bit better. All right. So we have an angle. Let's have an angle theta again. And I specifically want an angle theta that is too big to fit into a right triangle. So there's theta. Theta is greater than 90 degrees, too big to fit into a right triangle. What we're going to do is we're going to draw a right triangle by looking at this point on the circle and dropping it down to the x-axis, positive or negative. We're going to drop it down to what I call the nearest x-axis. Draw a line perpendicular to the x-axis from the point on the circle. So draw a line, connect the point on the circle. Yikes. We're going to connect the point on the unit circle to the x-axis. Connect the point on the unit circle to the x-axis with a perpendicular line. So drop this down perpendicular. So that point is still related to theta because theta determines where that point is on the unit circle. But theta is not going to fit into a right triangle. So what we do is we just drop a line perpendicular to the x-axis from the point on the unit circle. Now I can say that the radius of the circle is a hypotenuse of this right triangle. So we can see that the radius of the circle is the hypotenuse of a right triangle. So let's pull all these pieces out. I had the point on the unit circle. I drop that perpendicular down to the x-axis. I have the radius. And then the x-axis is down here. So here's the right triangle. I'm just gonna like copy and then paste it down into here. Everybody see where I got this right triangle? What we notice is that the radius is the hypotenuse, and this is a unit circle, so the radius is equal to 1. Because that's the hypotenuse, it's the radius of the circle. Also, we know that the coordinates of this point up here are x and y. So that point is on the unit circle, it has coordinates x and y. Smudge my right triangle. And we also know that this point is the origin, 0, 0. So we know we have a relationship between x and y and the 1. Here's x down here. That's this length. And then this vertical length is y. So this is how we're going to get a get a right triangle from the unit circle. Now, what we don't have is theta. Theta's like, all, hey man, where am I in all of this? And I'm like, oh, hang on, theta, you're always being so impatient. I don't know about theta on your end, but my thetas are always so impatient. We know that theta is way over here. That's the angle theta. And I need to involve theta somehow in this process. What we're going to do is we're going to take the angle between the x-axis and the radius of the circle, the hypotenuse of the triangle, and we're going to call that the reference angle for theta. So this angle in here is going to be theta sub r. Theta sub r is the reference angle. So all right, theta with the subscript of r, and that's going to be the reference angle for theta. Pronunciation guide. We make a subscript of r. So it'll be theta sub r. If you do an underscore, that'll make a subscript. And then we say, so theta with subscript r. That's not a letter. And you can pronounce that theta sub r. Usually, if we're going to be using a lot of subscripts, we're going to subscript a lot of our variables. We just start saying things like theta r. And we understand that our audience will know that we're talking about theta subscript r. But we want to say sub all the time, which is like, oh, theta r, because that's the cool kids. We use subscripts to list different values of a variable. So if I have a bunch of different values of x, I just start giving them number names. So x sub 1, x sub 2, x sub 3. It doesn't mean anything. It's just listing things out. When I write 2 in front of the x, that means 2 times x. When I write 2 as a superscript for the x, that means x times x. Sorry. So x squared. But when I write x with a subscript of 2, I'm just making a list. That's just the name of this particular x value. So x sub 1, x sub 2, x sub 3. Since we don't want to say sub all the time, We just say x1, x2, x3, x4. This is why your teachers were giving you such a hard time when you wanted to read x2 as x squared as x2. And they said, no, you got to say x to the second or x squared, because x2 is the shorthand language we use for subscripting things. We can always figure out what the reference angle for theta is, but it will change depending on what quadrant we're in. So the reference angle for theta changes depending on the quadrant. The way we find the reference angle, the way we find the reference angle depends on the quadrant in which theta terminates. The way we find the reference angle for theta depends on the quadrant in which theta terminates. So for the theta that we used for our example, theta ends in quadrant 2, and the reference angle just kind of goes the rest of the way. So theta r in quadrant 2, the reference angle is just 180 minus theta. So in quadrant 2, theta r is 180 degrees minus theta. So if theta is a 120 degree angle, 180 minus 120 is 60. That would be a 60 degree angle. We're just finishing off the straight angle. So in quadrant 2, theta r is 180 minus theta. What we need to do now is draw theta in each of the 4 quadrants and figure out how to find the reference angle based on the quadrant and the value of theta. So let's draw a theta in the 3rd quadrant. So there's one of them. In quadrant 2, the reference angle is 180, theta r is 180 minus theta. Let's draw another unit circle. And let's draw a theta that terminates in quadrant 3. A lot of times when I say, instead of saying theta terminates in quadrant 3, I just say theta is in quadrant 3. So when I say theta is in quadrant 3, I mean the terminal side of theta is in quadrant 3. Theta r, we drop, to find the right triangle, we go from a point on the unit circle and we drop down perpendicular to the x-axis. We always go for the nearest x-axis. And so we would have a different way of finding the reference angle in quadrant 3. So the reference angle in quadrant 3 for theta will go from the terminal side of theta to the negative x-axis. So here, that's where we're going to, here from the negative x-axis to the terminal side of theta, that's where we're going to find our reference angle. So all we need to do now is write down how we would figure out that reference angle, and all the rest of trigonometry will make perfect sense. Everything will snap into place, and we'll be able to finish this class in a week. All I have to do is right now tell you exactly how to find theta r when theta terminates in the 3rd quadrant. Once I say that one magical phrase, and as long as I get through it today, as long as I get that phrase out there today, then everybody will understand trigonometry forever. All I have to do is write down what it is right here. So I'm going to write it down here, and then we'll all be able to take the rest of the semester off, because trigonometry will just automatically make sense. So I'm going to write it down now so we all understand it forever. And oh, dang, look at the time. So next time, I'm going to need you to figure out what theta r is, how to figure out theta r as some function of theta when theta terminates in quadrant 3. And I also need you to do the same thing in quadrant 4. So I want you, not your assigned homework, but the place we're going to start talking, a thing that we're going to start talking about on Wednesday is how to figure out the reference angle based on a theta, based on where it terminates. So figure out how to find the reference angle for theta in quadrant 3 and quadrant 4. That's where we'll pick things up on Wednesday. Any questions? Great. That's going to do it for today, and I will see you all on Wednesday. Thanks for playing.